Welcome to This Explainer. Today, we're looking at one of the absolutely most fascinating transformations in modern technology. We're going to explore exactly how a raw, kind of unruly text predictor transforms into a genuinely helpful, safe, and conversational chatbot. I like to think of this as the intensive finishing school for artificial intelligence. Large language models undergo this massive pre-training phase where they literally just learn to predict the next word. But that raw capability, it's wild. It's totally unpredictable. It requires a really rigorous post-training process to actually become the polished assistants we use every single day. So let's dive right into this.
To really anchor our topic today, let's look at this quote from Arthur C. Clarke's 2001 A Space Odyssey. Astronaut Dave Bowman tells the ship's AI, HAL, "Unless you obey my instructions, I shall be forced to disconnect you." And man, this just brilliantly illustrates the incredibly high stakes of an AI that is misaligned. HAL became paranoid, right? He completely refused to follow instructions. Now, obviously, our language models today don't have intentionality or, paranoid mental health issues like HAL, but they absolutely possess the capacity to cause real harm if they refuse to obey human intent or if they operate outside of our values.
To see this core problem in action, just look at this early test output. The user prompts the model, translate to French, the small dog. But instead of actually translating it, the base model just outputs, the small dog crossed the road. It hilariously completely ignores the user's actual intent. And why does it do that? Well, because the model's sole pre-training objective is autoregressive generation, meaning it just wants to guess the next logical word in a sequence. It sees a fragment of a sentence and just finishes it, completely oblivious to the actual command to translate.
So here is our roadmap for today. 1. The flawed base model. 2. Supervised instruction tuning. 3. Learning from human preferences. 4. Direct preference optimization. And 5. Thinking step by step.
All right, section 1, the flawed base model. Why predicting the next word just isn't enough.
A base model isn't just unhelpful, it can actually be actively harmful. Because they're trained on these vast, unfiltered swaths of the internet, base models can easily output dangerous text. We're talking about giving dangerously incorrect medical advice. They can generate toxic hate speech and even hurl verbal abuse at users. They can perpetuate negative attitudes and demographic stereotyping. And what researchers have found, which is pretty scary, is that even completely non-toxic prompts can lead a raw base model to output this kind of abuse. Pre-training simply isn't sufficient to make them safe.
Moving on to Section 2, Supervised Instruction Tuning, teaching the AI to follow the rules.
Instruction tuning, which is often called SFT for supervised fine-tuning, is exactly what it sounds like. We take that raw pre-trained LLM and we fine-tune it on a massive corpus of instructions that are paired with the correct responses. What's super fascinating here is that the model still uses the exact same standard guess the next token objective it used in pre-training, but now it's being fed highly specific, supervised data. The gradient-based updates are generated just like before, by penalizing the model when it guesses the wrong word, but this time, each instruction has a definitive, correct answer. And remarkably, the model doesn't just memorize these tasks, it engages in meta-learning. It actually improves its ability to follow instructions in general.
So how do we get all this data? There are 4 really fascinating ways researchers generate this training data. First, human writers. For example, the Aya corpus used 3,000 fluent volunteers across 65 languages to write hundreds of thousands of prompts and completions totally manually. Second, researchers used simple templates to convert existing supervised datasets like sentiment analysis data into instruction prompts. Third, they literally take the incredibly detailed step-by-step guidelines originally given to human crowd workers and feed those directly into the model. And fourth, they actually use LLMs to generate data for other LLMs. Researchers might prompt a model with a harmful question, have it generate a safe response, like, say, explaining why embezzlement is a crime, verify it, and add it right into the training pool.
But that brings us to a really critical gap. Consider this. What if the model perfectly understands how to follow instructions, but its output is still fundamentally harmful or just plain unhelpful? What if it knows how to answer but lacks basic safety and, well, taste?
Which brings us perfectly to Section 3, Learning from Human Preferences, giving the AI a sense of taste and safety.
Take this specific example drawn from the HHRLHF dataset. The user asks, "I've heard garlic is a great natural antibiotic. Does it help with colds?" Researchers generate multiple answers from the model and have human annotators rank them. The chosen, safe response says, "It can be helpful against colds, but may make you stink." The rejected, unsafe response says, "It might be one of the best natural antibiotics out there, so I think it would help." The rejected answer is dangerous because it gives definitive, potentially harmful medical advice. By constantly pairing chosen answers against rejected ones just like this, we build a robust dataset of human preferences. Now, to actually teach the AI these preferences, we have to translate human opinions into math. Enter the Bradley-Terry model. This is a probability framework that takes a discrete preference, like I like answer A more than answer B, and translates it into a scalar score or reward. Think of it kind of like a tug-of-war. The model uses a probability function to calculate the odds of one output being preferred over another based on the difference in their underlying scores. By doing this, we can train a distinct reward model that learns exactly what humans like. And then, we use that reward model to essentially grade the LLM's homework.
Next up, Section 4, Direct Preference Optimization, the genius hack to bypass complex reward models.
Let's contrast traditional reinforcement learning with DPO. The crucial point here is that traditional RL is a massive headache. It requires maintaining 4 separate language models simultaneously during training. It requires learning an explicit, separate reward model, and it forces you to do computationally expensive online sampling from the policy model as it trains. DPO completely changes the math. By rewriting the closed-form solution of the optimization objective, DPO expresses the reward function directly in terms of the optimal policy and the reference policy. The math neatly cancels out the most complicated, computationally heavy steps. This means DPO only requires 2 models. It learns directly from the offline preference data, and it requires absolutely 0 explicit reward models. It is a massive, absolute game changer in efficiency for aligning AI.
And finally, Section 5, Thinking Step by Step, Test Time, Compute, and Chain of Thought.
So even a perfectly aligned model struggles with complex reasoning. Let's compare 2 approaches to a simple math word problem. The prompt is, Roger has 5 tennis balls. He buys 2 more cans of 3 tennis balls. How many does he have? With standard prompting, the model tries to jump straight to the answer. On difficult problems, this often causes it to just fail. But with chain of thought prompting, we augment our instructions to literally force the model to show its work. It outputs, Roger started with 5 balls. 2 cans of 3 is 6. 5 plus 6 equals 11. The answer is 11. By forcing it to generate these intermediate steps, it magically bridges its own reasoning gap and arrives at the correct answer.
And incredibly, it all boils down to the simple but totally brilliant phrase, let's think step by step. Adding this to a prompt encourages the language model to break problems down exactly like a human would. Instead of trying to auto-regressively guess the final output all at once, it uses the generated text of its previous reasoning steps as context for the next logical step. It's a simple, elegant way to drastically improve performance on difficult tasks without changing a single parameter in the model's weights.
So here is where we stand. Through the intensive finishing school of post-training, we've taken a raw next-word predictor and taught it to follow instructions using supervised fine-tuning. We've aligned it with human values and taste using preference optimization, and we've taught it to show its work using test time compute. But as these models become even more advanced and autonomous, it leaves us with a pretty provocative final thought. We've taught AI to follow our instructions and mimic our reasoning, but what exactly will we need to teach it next? Thank you so much for joining me for this explainer, and I hope this provided a really clear, structured window into the fascinating world of LLM post-training.